Can you see my screen again?
Yes, but not full screen.
Not full screen. Yeah. Stop sharing. Let's see, let's do it again. How about now?
Now it's okay.
Okay, thanks. So, okay, people, we're going to continue to complete this deduction, okay? So we have two expressions for the conservation of mass. One is the integral form, the other is the differential form. Let's work with the differential form just a little bit and see can we get something else. Okay, so we have the derivative in differential form. We have the derivative of rho with respect to time plus nabla dot rho v is equal to 0. So we consider now it's one of the cases, one of our favorite cases. So we said in case we consider rho is a constant. Okay, so this is typical of liquids. See, for example, liquids. Okay, if this is true, then this derivative is 0. Okay, so we can say that this, but now this is constant, so we can take it out. So we can say that this is true equal to 0. So since rho is never 0, the only way this is satisfied is this. Some people call it continuity equation. Okay, so if we recall, nabla was the expression for nabla, and v, it's we can express. So we can say if we express, we can say, for example, that v is equal to u in the I direction, v plus w k. So it's the three components of the velocity. So continuity, nabla dot velocity, will give us the derivative of u plus the derivative of y and w, they have to be equal to 0. So, for example, if we consider that in a 2D case, for example, see in a 2D case, right? So let's suppose I have a velocity here, and we have an increase in velocity. So this is u, and of course, this is x and y. So here, I have du dx dx. Okay, so this du dx, let's suppose it's positive, right? And you see that the velocity here is larger than in here. That means that in the x direction, okay, the mass is going out of v. So in x direction, mass is flowing out of dv. Okay, so that means that inside we are losing mass, but the problem is that the density in here doesn't change. What do we need in order to keep this equality? Well, what we need is that in the y direction, we have a v here and a smaller v in the other side. So it's v plus dv dy. And you see that when I consider the change of this v up to this point, I'm moving only in the y direction. So that's why the change in v considers only the rate of change of v in the y direction. Okay? So dv dy has to be negative to keep rho constant inside dv. Okay, so it's in one direction, we have a rate of change which is positive. That means that the water is, or I'm sorry, the fluid is going out in the x direction. In the other direction, we have to have an entrance of mass so that the mass of fluid inside dv keeps constant. Otherwise, we're going to lose mass, and that's not possible. Okay? Now, this is just the physical explanation of what do we mean by this expression. And it's easy if we could explain it using that the density is constant. When the density is not constant, well, the explanation is a little bit more complex. Similarly, when we have to explain it with three directions. So that the 2D case, rho constant is easy to explain. But it's useful to understand physically what this continuity means. Now, this is another case, okay? And in this situation, we have to use the integral. Version of the conservation of mass. Okay, in this case, we are considering the steady flow in a tube, but in A1 and in A2, the areas are not the same. Okay, so in this case, we have a steady flow. If we have something steady, that means that there is no rate of change in time. So the derivative with respect to time of any variable is equal to 0. So the integral of d rho d time plus nabla dot rho v d v is equal to 0. So this is going to be 0 because it's a steady problem. And this integral, okay, we can put it back using Green theorem. Okay, this is an integral in volume, so we can put it back to integrate the surface limiting the volume. And in this case, it's going to be what? It's going to be rho v dot n ds is equal to 0. And this term here does not participate because we already said that it is an steady case. Again, we can go on with and say that the integral over the whole surface, we can integrate it on S1 plus the integration of S on the sides, and finally on the out, which is S2. Okay, in each one of these, we can assume, it's typical, that V is uniform in any section. Of course, this is a huge assumption, right? Because of course, we know that if we have viscosity, then the velocity is going to decrease, right? If we have a tube like this, we consider a certain section here, the profile of the velocity is going to be something like this. But for this analysis, we're going to say that we consider that this is the way we are going to consider it. It's like an average at any position, right? So the flow here is going to be simply this average times the area. Otherwise, we will be in trouble, really. So for S1, okay, we have something like this. This is V, this is S, and this is N. For S, for the surface, for the sides, right, we have something like this, and this is the velocity, and this is N. They're going to be orthogonal. And for S2, we have something like this. Here we have N. So this is, I'm sorry, this is V, this is N, and this is the velocity to the right. Okay, so in this case, this product V dot N, so here V1 dot N, see, both have the same sign. So it's going to be simply V1. And here, V side dot N is 0 because they are orthogonal. And in here, V2 dot N, see, N is in this direction, V is in that direction, so it's going to be minus V2 times 1, because we assume that it's uniform. Now we can proceed to integrate. So the integration over the whole surface is going to be, so this is going to be rho, which is constant for the whole integration. And here we have the area A1 and V1. Then on the sides, the integration gives us 0. And on the right-hand side, the result is negative. So we say this is A2, B2. And the result has to be 0. So rho is never 0. So we have to have, I'm sorry, this is B2. So since rho is never 0, so we can say that V2, this one here, is going to be A1 over A2 times B1. It's something that we know. I just wanted to remember these things. So we can say that as A2 increases, we can expect a reduction in mean velocity. That's something that we know, right? Questions, people? Questions? Questions? Okay. So I'm going to stop here. In the next session, we're going to be working with Laplace's equation. And that's to start that, we're going to say from the very beginning that we are not going to include viscosity, okay? And you immediately think, wait a minute. We're going to have very poor results. Yes, up to a certain point. There are certain phenomena which are very well analyzed, very good results with neglecting viscosity. And one of those is the waves. right? So you can analyze waves using Laplace's equation, which is a consequence of potential flows or non-viscosity. There are some others which we have to be careful. For example, when we analyze the roll motion, okay, you have the ship and it's rolling, okay, and the damping, the generation of, well, the friction, generation of eddies and all of that, man, we have to include viscosity in that case. So what we can do in that specific situation, you will see in chapter 4, is that we consider that the damping is formed by two factors. One is the damping, which is related to potential flow, that's generation of waves, and an influence from another component which suffers the influence from viscosity. And we obtain those from experiments. But that's what's coming next week. Now, please, everybody turn on your cameras. I want to see your faces. I want you to raise your hand. Who has opened the module 4 to learn Excel? Raise your hand. That's something that you have to do. Okay. Not many. What happened with the rest of you? Mr. Barba, what have not started the training in Excel? Mr. Barba, are you there? Mr. Barba, hello? Mr. Barba? No? Mr. Zamora? Mr. Zamora, are you there? No. Matute? Hello, Matute. Where are you, Matute?
Hello. I start and don't end.
You started Excel?
Yeah, in the module
Okay.
2.
So the thing is this, people. We have seen that you spend too much time trying to learn Excel. And yeah, it's a good idea that you learn Excel, but what we need is that you have Excel available. So what you have to spend your time is in analyzing results. Okay, that's what I try to put it at the very beginning of the semester. I wish I had done this 1 week before we start the semester, but that's the point. From here, you will go on to the final process for graduation, and you need to handle a lot of information, lots of data, and for that, it's quite useful to have Excel. Okay, now let's go to, please lower your hand. Now, let's go now to the homework. In the homework, we have 2 problems, okay? The first one is about the simple pendulum. You have to deduce the equation of motion, considering different situations, considering the reference point at different points, okay? Have you started the homework? I'm sorry, problem 3. Raise your hands, those of you who have already started. Problem 3. Okay. I was going to say, Mr. Mendoza, what happened with, no. Mr. Zamora, what happened with you? You haven't started problem 3 about the pendulum? Mr. Zamora, are you there? Looks like we have problems. Okay, so everybody else is doing good. Lower your hands. How about problem 4? The problem 4 is very interesting because we're going to do tests with this system. And eventually, you are going to compare your results with those from your calculations. Okay, now, Who has already calculated the natural frequencies of problem 4? Natural frequencies, who have calculated already? Okay, I have one. Okay, nobody else. Mr. Ramon, how far have you come into problem 4, in solving problem 4? Mr. Ramon, how far have you gone? Mr. Ramon? Mr. Ramon?
Okay, doctor, you listen to me?
I mean, there are certain steps in solving problem 4, okay?
Okay, I do only like the equation on motion yet.
How many equations of motions do you have?
3 equations.
Ah, okay, I thought it was 4.
No.
Okay, Miss Lopez, Michelle Lopez, are you there? Miss Michelle Lopez?
Yes, doctor.
Okay, what have you done about problem 4?
I
You
I
haven't started.
complete the question for the first case and
Okay.
and free and the second.
But hold it.
Oh.
So you have the equations.
Mhm.
What's the next step after having the equations?
Obtain the matrix dynamics.
Okay. Did you
Uh,
have the matrix? Do you have the matrix?
Yes.
Okay, now what else after that?
Obtain the natural frequency.
Okay, good. After that, Mr. Matute, what's next?
The other friend has obtained the shape mode.
The mode shapes, yes. Okay, now that's the steps. Okay, so there should be no doubt. Okay, now, did anybody get I mean, there are some people who said that they obtained the equations of motion. In the equations of motion, were you able to identify the equivalent excitation? Anybody? Equivalent excitation. No? Okay. Finally, okay, there's only one person I'm not going to ask. Okay, let's go on. Now, people, in this case, okay, I suspect that it is a good idea if you start learning in Excel how to handle complex numbers. Okay, you can do it by hand, I know, but the problem is that it takes too much time. Okay, so my suggestion is try to learn how to handle complex numbers in Excel. There are certain basic operations with matrices that can be developed with Excel. So my suggestion is try to learn those. Otherwise, you're going to spend too much time solving this problem. So complex, do you know how to set a cell with a complex number? Does anybody know how to do that? Enrique, do you know how to do it? No? Gutenberg, do you know how to do it?
I understand that if I can put in Excel the complex numbers, yes, I do.
Would you please repeat, because your microphone is a little bit low, so
Sorry, I understand the question if I can put in the Excel the complex numbers, right?
Yeah, no, but you have to use a specific function. See, what you have to do is you have select a cell and put some information, so Excel recognizes that as a complex number.
Yes.
Does anybody remember how to define a cell with a complex number? I'm not going to say it to you. That's what I want you to have this module. Okay? You find out. And then, does anybody know how to calculate the determinant of a matrix in Excel? How to calculate the determinant in a matrix in Excel? Mr. Galarza, you never calculated the matrix in Excel the determinant of a matrix in Excel?
I have to remember, Doctor.
Your vacations were very good. Good. Mr. Zambrano, do you remember how to calculate the determinant of a matrix?
I did it in Final Elements, but I don't remember the function. But
Ms. Vega, do you remember?
M determinant the function.
There you go. M determinant or something like that. This M is the matrix determinant. Parentheses, and then you select the elements. Close, enter, and then you will get the value of the determinant of the selected area where you have the matrix. See? So there are many operations that can be implemented using Excel. Now, similarly, for example, if you want to calculate the inverse, there is a function in Excel to calculate the inverse of a matrix. You want to calculate by minus? Okay, do it. You can do it, yes, but it takes a lot of time. Especially, people, pay attention to this, especially because I don't want you to calculate the force response for one single frequency. I want you to vary the frequency. It takes many values, and then you can plot and recognize the resonances around the 3 natural frequencies. Remember, that's what we observed in the video from Engineer Isaac. Every time the motion of the foundation has a frequency which is closer to one of the natural frequencies, we have an increment in response. That's what you have to calculate using your equations. And eventually, we're going to be able to compare that with experiment. Okay? Okay, people, it's 5:31, so it's 1 hour and a half. So is there no more questions? Then I'll see you Tuesday, okay? Your class notes hopefully will be ready for, I don't know when, hopefully by tomorrow afternoon, but